So the first thing I want to bring to you is what is sharding. How did this word became the new thing in blockchain technologies, and why it's really necessary, sharding protocols. Hello everyone, today I'm going to explain a little bit about sharding, what is sharding, why it matters so much, and why are so many protocols discussing the architecture based on sharded chains. So before I speak a little bit of Greek, let me try to explain to you in a simple way what is sharding. And I like to relate a lot sharding to shredding. I think I heard somewhere that connection and I thought it was pretty cool. Well, a shredding machine, what does it do? It divides the paper, it destroys the paper, but it destroys the paper in specific number of sets of smaller pieces of paper. So if we want to rebuild the piece of paper, we put them all together again. And if we imagine the same with computational power, we can also divide computational power into different shards. So every time I think about shards, I think about those little pieces of paper where everyone is significant to make a whole thing together again. Sharding is this promising way to scale distributed ledgers. We're going to divide, instead of every transaction passing through a whole set of validators, we divide this network of validators, and they can be divided into those subgroups, and we call those subgroups the shards. So what do validators do? Validators validate. Oh, so stupid. Yes, but that's exactly what they do. So validators do that in two different forms, as you probably know, through proof of work, where they use a computational power, where they use electricity to calculate the nonce of the next block. So they all get connected into this network, and they calculate that computational power to know, to validate transactions and to guess the next block. Or they can also do that through proof of stake, which is a way that validators delegate their vote, so other people and other supercomputers can check if those transactions are valid or not. The more computational power, the more secure the network is. And also important to say that the more decentralized this network is, the safer it is as well. Why? Because we have more computers making sure that one transaction is going to be checked by more people. Just like in statistics, the higher the set of people that we're going to interview, the more we can rely on that information. So if only 30 people decide an election of a country, it is very insignificant when we have an election that, let's say, 10 million people voted. So it's more, significantly speaking, interesting when we have more validators or more voters to check the accuracy of a transaction or of a vote. So what does sharding do? Sharding does this division. Instead of everybody, let's say 10 million votes or 10 million transactions being checked by 10 million people, we can divide that into sets of 1 million people each. Now, what happens is that security can be compromised, because if one of those sets of validators corrupts the shard or that subgroup, then the whole network is not secure anymore. And it's technically way cheaper to corrupt one single shard than to corrupt the whole network. You need to deploy a lot of money, a lot of computational power, a lot of machines, and a lot of electricity to corrupt a big network, for example, like the Bitcoin or Ethereum. However, if they shard, once you can corrupt one shard, then the whole security of the chain is gone. So that's why security in each shard matters a lot. Now we're going to look about who chooses the validators for each shard. Some networks, they delegate specific validators to each shard, and others are assigned randomly. So randomly is also good because you don't know exactly if, let's say, if you have a set of malicious validators together, if they all decide, okay, let's do bad things in that shard, if they collude, they go together and they corrupt one shard, then the whole network is gone. But if they don't know and the three of them are in different shards randomly assigned, then their power is way less powerful together because they're now divided in different shards. So almost all sharded architectures, they rely on this randomness of shards. This randomness is a big challenge for most blockchain architectures. And I'm going to divide them into different groups, where we have in one side Ethereum and Near protocol. They have something called the beacon chain. That's what they call this blockchain that has some admin features. So there is a specific group of shards, but there is one of them which is the beacon chain, and I like to call it the admin chain, to make it more simple. So all the validators, they go through the supervision of this beacon chain. In Cosmos, they call it the Cosmos Hub, and in Polkadot, it's also called the relay chain. And they have some features in this beacon chain. One of them is to generate random numbers, so you don't know where you're going to validate. And then the second thing is they assign where each validator is going to go. So all that happens because there is this master, more powerful chain with admin features. The second thing, the beacon chain also receives updates from shards. It also takes snapshots of those shards from time to time. So it's very important that you know exactly what happened in what time. And they also process the stakes. So if there's a lot of validators in one shard, they also process to make sure that they get divided randomly, but they all separate in a meaningful way. And they also have the capability as an admin chain or as a beacon chain to slash the validators in the proof of stake system. So they have this power to see if you're a malicious shard, then you're going to be slashed. And also the rebalancing of shards. So to make sure that each shard is not only in one, each validator is not in only one shard for a very long period of time, because they can get friends and they can collude and then can say, okay, let's double spend here. So the longer they stay in one shard, this can also present as a risk. So they have to change the validators, they have to move shards from time to time, as if they don't know, as if a child changes school and all of the blue you go to a different school. So it's gonna take some time until you have your new friends. And the same happens with the beacon chain. What they do is to divide those shards from time to time. Any solution that has a beacon chain, it's not going to have infinite scalability. So people have this misconception that sharded chains or provide infinite scalability, and that's falsely advertised. Unfortunately, the beacon chain in the end, or this admin chain, is the bottleneck, because it does a lot of the computing power that needs to be revalidated or double checked. If something is going wrong, they need to pretty much supervise that. So that becomes the bottleneck of the system. As I was saying, this bottleneck of computing power of the beacon chain is not only but an amount of booking and snapshots of the computing power, and this is proportional to the number of shards in the system. However, this is limited to the computing power of the nodes operating it. So if we have less powerful resources, if they don't have, let's say, if they all operate under a processor which is a Pentium, is not even an Intel i7, for example, so they're going to go slower. So this limit of processing power is, it comes from all the validators that are processing these operations. So the power of the nodes operating the beacon chain matters a lot, because if your admin is slow, it doesn't matter if you're fast and you produce a lot of transactions fast, because they're going to take forever to take that snapshot of what matters and what doesn't. So if the nodes in the beacon chain are 4 times faster their ability to process is 4 times more transactions. So the beacon chain will be able to maintain 4 times more shards, though it increases by a factor of 4, and there comes the term quadratic sharding. So what is quadratic sharding? Quadratic sharding is if the nodes operating the beacon chain are 4 times faster, they have the ability to process 4 times more transactions, and then they will be able to maintain 4 times more shards. So hence the term quadratic sharding. About state sharding or sharding of storage. I would like to remember you what is the function of a node. A node has basically 3 functions. One of them is to process the transactions. The second function is to relay the validated transactions to other nodes. And the third is to store the state and history of the entire network ledger. So the nodes do those 3 things. As the network grows, they need to grow on computing power to process transactions. However, they also need more bandwidth, more Wi-Fi in the network to relay, because again, it goes through bottlenecks. So if you have a slow connection, a slow node, and that slow node needs to process that transaction, the whole network is going to be subject to the speed of the bandwidth of that node. And the third thing, as it grows, the network needs more storage space, of course, because the ledger is going to be way bigger, and the transaction growth is also going to grow together as this ledger grows. So the storage requirement is going to grow as well. Zilliqa does sharding of processing. So it's an easier problem to solve because each node has the entire state, they have the entire ledger already. So it's a very simplistic approach because we can shard the processing power, we can shard the ledger, and the difficulty is specifically on sharding the transactions, power of validating them. Cross-sharding. Cross-sharding is something that can be synchronous or asynchronous. What is a synchronous cross-sharding? Synchrony, well, it must happen at the same time. So it's a project by Vitalik Buterin. You probably heard about this very smart guy. And the proposal is called merge blocks. So blocks that contain the state transition related to the transaction get all produced at the same time. So if I'm doing a transaction from Alice to Bob, whoever is validating this transaction will get done or will process at the same time, synchronous. When it's asynchronous, you have a cross-shard transaction. So a transaction must move shards. It must go from one shard to another shard. And that happens in different periods of time. So that once that transaction needs to cross shards, it affects multiple shards and it's executed in different timings. So you might be done in one shard, but the other one hasn't. You have to get on the line on the other. So it cannot say, hey, I just sent you, but then there's a gap for the other one to say, hey, okay, got it, I just received it. So you have a debit shard which executed its portion and it's easier to coordinate, and a credit shard that is already executing its part only if it has sufficient evidence that the debit shard already executed its portion. So as if just pass the transaction to me once I know you did your job to validate it properly. But before I can be sure, I need to check. So it can only start validating after you're finished. So this happens in different timings. And asynchrony is proposed by projects like Cosmos, Ethereum, Serenity, Near Protocol, Cadena Protocol, and others. The problem is that if blocks are produced independently, there is a chance that one of multiple blocks will be orphaned, so making the transaction only partially applied. So now I want to explain something about the trustworthiness of a blockchain. And it's very important that we don't have a specific number of trusted nodes. We can have 10,000, 10 million transactions per second and say, wow, that blockchain is super fast, it's scaled very well. But 10 million transactions per second means absolutely nothing if we cannot trust the validators. That's why security matters very much. Whoever's verifying those transactions are always going to be the bottleneck, and that's why this question is so, this issue is a very difficult issue to deal with, because we need a lot of trusted validators, non-Byzantine validators. So let me give you an example. Let's suppose we have 10 out of 100 validators, and we know that those 10 are malicious or Byzantine. So if we divide those 10 malicious or Byzantine validators in a structure that had 100 transactions, 100 validators, but if we divide them in 2 shards, we're going to have 50 validators to each side. And then if we put 10 of them, let's say by random chance, all of them go to shard A. Let's say we have shard A and shard B. We put them all in shard A. What will happen is that still 10 out of 50 is 20%, and 20% is still below the maximum capacity to be Byzantine fault tolerant, which is usually 1/3 of malicious nodes. So this is still secure if we have 2 shards. However, if we have from the 100 validators, if out of the blue we're going to have 100 shards, and by random chance we're going to have 1 validator in each shard, we know that 10 of them are Byzantine. So 10 are insecure shards, correct? Because everything that gets processed in those shards are going to be faulty and non-reliable transactions. So they're going to double spend as much as they wish in the shard that they are. They are the only validator over there, so they have 100% of the shard. And that makes the whole architecture gone, because it doesn't matter if you have 100 shards, you cannot trust 10 of those shards, you cannot trust the whole network. Even if you have 1 shard out of 99, if that 1 shard is corrupted, that's it, it's gone. So that's why the number of shards matters so much. And this is not, again, as I explained before, it's not infinite scalability. We have a limit of a number of shards that we do have to have. In most blockchains, they don't have that final number of shards. As the network grows, they grow the number of shards. We're going to see a little bit later how that really poses as a problem as well because of distribution. And also statistically, if we don't know how much is the whole sample of shards or how much is our universe, we can also have a mathematical equation problem. And that's why most blockchains, they took some approximations to calculate and to expose to the market why their security was something concerned. And a lot of them did a binomial approximation, which is not really good, because a Byzantine fault tolerant, a validator, with a given fraction of voting power in the network have a large influence by a random chance, as you're only sampling a small portion of the population. So let's say if you have 98 million shards and you only take 2 of them, so the sample is significantly small compared to the whole universe. And you have to make sure that everything are accounted into place, because again, 1 corrupted shard means it's over. So that's why many blockchains decided for the architecture of always having a beacon chain. And in the end, the beacon chain may be super powerful computers and a lot of processing power, but they will still be the bottleneck, because they will still depend on the number of transactions that they can process, the number of snapshots that they can take, and things like that. So binomial approximation for calculating the malicious nodes and shards is something unacceptable according to some blockchains. And they reduce the economic power, directly securing the network. Binomial distribution is also not a good estimate indicator for the probability of failure in the sharding. And some projects are using binomial distribution without replacement. So the thing is that it's not that you just pick a shard, but then you have to randomly reassign them. So as if you replace the dice of this calculation. So it's important to do this replacement, and it's a statistical method to estimate the number of Byzantine validators. So they claim that they are secure, but technically, statistically, they didn't do the replacement of validator nodes. Why do I say replacement all the time? Because in one day, you're going to be validating shard number 23. The other day, you're going to be validating the shard 57. So if 57 already has 2 or 3 corrupt validators and you go there and you join them and you collude, and out of the blue you have more than 1/3 of the processing power of that shard, then you guys can corrupt that shard, and the whole transactions happening over there are malicious, and then you cannot trust again. So the fact that you're randomly always assigning, it helps because you never know which kind of friends you're going to have, which kind of other validators you're going to find. However, you need to statistically also do this reassignment and resampling of your whole universe. And so one blockchain deserves attention because they are doing the binomial distribution sampling to calculate the probabilities of corrupted shards, and they're doing that with replacement. So considering that nodes and validators are going to change shards over time, and that is Cardano. And Cardano uses a conservative churn-off bound, which is not really accurate for hypergeometric distribution, but multi-chain and CryptoTask also assume some incorrect sampling replacement. So some other blockchains are doing hypergeometric distribution. And if you're a statistical guy, I really appreciate if you could comment on why hypergeometric distribution matters so much, and why they are a more accurate way of calculating the security of a network. So that's the beauty of blockchain technologies, is that you connect not only mathematics with game theory, with computational power, with code, with economics, with corruption, with money, with people, with sentiment, with everything together. So seriously, I really appreciate if you're a mathematical, statistical guy, and if you could explain a little bit more why the hypergeometric distribution matters. And if I can, I'm also going to put down here in the comments some good posts that I read about hypergeometric distribution. There is a network called Logos, and one of their claims is that they're doing this kind of testing before they implement the architecture that they're promoting. So keep an eye on those guys as well. Logos Network is also someone that is doing this statistical concerns before they build the architecture. And in the Definity white paper, also important to say that they define the security approach that each group or node is honest. So you'd already come with the assumption that each one is honest. And then they use cumulative hypergeometric distribution for this first group. And this is good, but if you only, let's say you do a good proof that you're only going to bring in honest people to your network. Honest people, don't forget, they can also be corrupted, and nodes can always change their behavior over time. It's a matter of fixing the code to make malicious transactions true. And you cannot assume that people can and will remain honest during the period of time of the network, which I hope is going to be a long one. So these are some of the issues that blockchain technologies are trying to solve every day. And that's why so many technical people are needed to help in this network to make sure that it's safe, not only that it scales, but that it's safe. And safety matters a lot. As I explained, one shard, it's all gone. Rapid chain paper, also written by the Definity researchers. They make the same mistake. They assume that everybody's honest from the beginning, and it's good. If people keep honest, that works. But if they become corrupted over time, then the whole assumption is over. So this is acceptable. A lot of things are acceptable in the theory, but when you develop a rough intuition of the number of nodes to require to process the network, then the history changes a little bit. It is a serious risk of practical deployment. A public decentralized blockchain needs a deterministic way of setting the number of shards. You need to know that beforehand. You need to determine, so you need security before you build the architecture. As a function of the number of nodes that changes dynamically over time. And the precision of this calculation has a big impact on the network's practical security. So again, a public decentralized network needs a deterministic way of setting the number of shards as a function of the number of nodes that changes dynamically over time. So the more shards you have, the more nodes you have, the higher it grows. And it's very hard to determine what will be this final number. So this precision of this calculation has a big impact on the network's practical security, because on theory you can build any architecture that you wish, but in practice it really matters to be the more precise as possible. And a very interesting architectures that I saw is on Radix network. And Radix is building a blockchain that already has a finite number of shards, meaning that they will have 2 to the power of 64. I don't know exactly how to say this term, but I believe it's 1 quintillion shards. And it's a very big number of determined shards. So they will always know how big is their universe. It's a pretty big universe, so it's a very likely scalable architecture that they're building. But the beauty of it is that they know what is their final numbers. You're not going to have 1 quintillion and 1, for example, 2 to the power of something else. It's going to be a maximum of 2 to the power of 64. And also, if I'm not wrong, they did that because they took the whole storage power of Google today, and they considered that Google is probably one of the biggest processing of information or data centers that the world has. So they took that as an example. And they're building a very interesting project. I really suggest that you go there and check. It's radixdlt, if I'm not wrong, .network. And congrats to the team as well. Did a very good statistical review and a lot of material. If you're interested, that's a pretty interesting blockchain to check the architecture. Ethereum sharding could be safe if the number of nodes is at least 150. That's some assumption that someone did in the chat. The error is calculating and estimating the correct probability for the first shard to be safe. But it is not the same probability for all the shards. So you calculate for one shard, good, but you need to calculate for all the other shards. And there is a script in Python that for the GitHub lovers, I'm going to put the link also down here, by Michael Skochovsky, excuse me if I pronounced it wrong. Michael did a calculation of the sharding failure rate. So he did a Python script, and it's very nice for you to input the number of shards that your network is going to have, the number of probable corrupted validators, and then you can calculate the probability of an attack, which is good, huh? So guys, it's all open source. Very, very big thanks to Michael for putting this up to the world. So a big applause, congratulations for the open source spirit. It's always very nice to exchange thoughts with brilliant people like you, Michael. And it also calculates with the probability replacement. So this Python script is very nice because it calculates without the probability replacement and then with the probability replacement, which is when you take the without replacement, you have to use hypergeometric distribution. So it's all there, check it out. github.com, M. Skoczowski, articles, blob, master, sharding, and then you're gonna find this. Sharding attack probability.py for Python. And so how many shards can a network have? It really depends on how many total nodes we're gonna have, how many do we assume are gonna be malicious or Byzantine, and the whole risk tolerance of the network. Usually, if it's Byzantine, the market convention is 1/3, but maybe in some architectures they decide to push the bar a little bit higher, and then let's say they need 40% of the network to be considered safe. So the considerations of safety right now is that you can still operate if 1/3 of them are malicious, but the risk tolerance can vary. Don't forget that it's all not just one size fits all in blockchain. Each architecture is being built in different ways. And rather than determining the number of shards based on a strict formula shared by all the nodes, it makes most sense to have some sort of decentralized governance mechanism that allowed nodes to come to consensus on the number of shards. So this allowed the nodes to reflect their own independent calculations, which may incorporate more sophisticated information and criteria, as well as their own risk tolerance. So that was it for today. Thank you very much for watching. I will try to bring as much knowledge as my brain processing power can bring to you. I'm not a pro, I'm not a mathematician. I studied a little bit of statistics, and I always suggest that you read a lot and always criticize what you're reading. Do not trust your ICO advisor. Please do not. Do your research and study the more that you can infrastructure, because infrastructure matters. If you're going to trust a network and that network is going to be corrupt, it's all gone. So I hope you can count on me for this journey. It's a wonderful journey, and stay tuned. If you like this video, please give me that thumbs up. I will appreciate that, because that's the only way that information is going to be passed. Thank you guys. See you next time.